This is chapter 4, which is actually supposed to be for today's lecture, Tuesday's lecture, the latest Tuesday lecture. And here we are going to be talking about tribology, metrology, and product quality. And if you remember in the last class that we talked about one of the most important properties that we need for materials is its fatigue resistance. And how do you improve the fatigue resistance? You have to do a lot of different kinds of surface treatments such as case hardening or iron nitriding or short peening, etc. All of that improves the fatigue resistance of the components. But how do you correlate that to the surface quality? So if you look at the surface structure, a cross section of the surface of the material, you can identify different thicknesses to the part. And if you see that the topmost layer, which is approximately 1 to 100 nanometers, you have containment, and while you are doing this, there might also be some adsorbed gas and things like that. If you have some kind of case treatment that you have done or heat treatment that you have done, there could be some adsorbed gas. Then you can have an oxide layer, and you might also find some amorphous layers, and you might have what is called a work hardened layer, and then at the bottommost layer is the substrate material itself. And the thicknesses of the individual layers will depend upon how the processing was done and what kind of environment was used to process these materials. Okay, and how do you correlate the surface finish of the material? Those are based on the um, the surface finish, which are determined by different kinds of methods, and we will describe those as we move along. And these are described in terms of the roughness of the surface. So if you have say a case hardened structure, or if you have a polished ground surface layer, that would have a much better, um, much improved surface roughness compared to um, compared to the um, the uh, compared to the determination, the technique that is used to determine the surface roughness. So you can, this is actually an exploded image. You can see that even though you might have, by for to the naked eye, it may seem very smooth and uniform. You may find that the surface might actually be, if you look at it under magnified imaging techniques such as the scanning electron microscope, you will see that there is a kind of a waviness, um, and there could even be flaws and things like that uh, on the surface. So if you in order to do that, you have to measure what is called the surface profile of your uh, material. And you do that, you describe that in terms of an average number. So that is typically called root mean square roughness, or RMS roughness. Okay, so and each of those have some kind of a cutoff uh, information depending upon the roughness. So if you have a very smooth surface, then that RMS value might be less. If you have a very rough surface, then you might see that it is up in one side and down on the other side. So on the average, um, that number could be pretty large. So the larger it is, the rougher the surface is. The lower it is, the smoother the surface it is. Okay, so and you may also find some kind of a waviness, etc. So that height is described in terms of some numbers. So this is all in terms of microns. So it could even be in terms of nanometers. So nanometers is less than microns, so which is a better, lesser surface roughness compared to, say, a machine surface. I hope you are understanding what I'm talking about here. Okay, so these are the what is called the surface lay symbols. So this would be laid parallel to the line representing the surface to which the symbol is applied. Or you could also lay it perpendicular to the surface to which the symbol is applied. So you can have multiple ways in which you can represent that. Or you may also do a cross hatching, or you might do it for non directional in nature. So these are the lay symbols. So if you incorporate that in the under square root, so this is called the root mean square number, and it can be done in terms of parallel to the line, perpendicular to the line, or it could be cross hatch, or it could be non-directional in nature. So each of these is determined at what is the height with respect to the base height or the average height. You represent that, and you take the average over a particular length. So you have a center line, and the values are determined with respect to that center line, whether it is up or down. So if this value, the difference between the top and the bottom is pretty large, that means this is not very smooth. But if that number, the average number, comes closer and closer to zero, that means the average root mean square root mean square number would be pretty low. And you have similar um, numbers that are used, say, for flow rate and things like that. So there you talk in terms of root mean square velocity of the flow rate. So similarly, you have root mean square surface roughness of your surface, of the machine surface. And how do you measure that? You have some kind of a stylus, and it would be moved on top of the surface, and it would plot that value. So the actual surface might be slightly different with respect to the stylus path, and it would measure that and give you the profile as a spectrum. So this is how it will look like. Okay, so you do that in terms of the length. So these are the typical surface profiles produced by lapping, finish grinding, rough grinding, and turning processes. So you can see that lapping would give you an extremely smooth surface finish. Finish grinding would give you similar, but it is not as good as lapping. Then you have rough grinding, and if you have just turned surface, then you are going to have tremendous roughness on the surface. So depending upon the quality of your part required, you have to use different manufacturing processes. So you have to choose the right kind of finishing process for your component. So where does this come? I mean, so suppose you have two surfaces that have tremendous amounts of surface roughness. So when you are trying to move them or scratch them, I mean, or move them on top of each other, you're going to have a lot of frictional forces that are created. Okay, and sometimes because of the contact stresses, you might even have considerable heat that is generated as a result of the actual component service. So your friction force is going to be dependent on the amount of contact between the two surfaces that are moving in relation to each other. So that is also going to be dependent on the normal force that is applied by one surface on top of the other. So if you have different kinds of manufacturing process, you're going to have a maximum that is going to be generating that friction force that is going to generate that. So it is the highest if you have drawing or rolling and things like that. It will be less. So the smoother the surface, lesser the frictional force. And if you have lubrication that is being used in the um, during the manufacturing process, or uh, so this is also going to generate the type of profile that you will see in your final part. So you know that when you are trying to compress something into a final shape, you are trying to avoid barreling if at all possible. So if you have good lubrication, then you would avoid the barreling. But if you have poor lubrication, then it is going to generate a lot of barreling in your final part. So poor lubrication is not as good as good lubrication in your part manufacturing process. So you can see that there is something called frictional factor, and you can determine that from these charts given in this slide. Okay, so from that you can determine what is the manufacturing process, um, what are the conditions in the manufacturing process that you need to adopt in order to avoid the barreling phenomenon during the manufacturing. So if you have asperity, I mean, what is asperity? Asperity means the up and down nature of your surface. So if you have too much of those up and down, then you are going to be creating considerable friction. And you might even, I mean, especially if one material is softer or smoother with respect to the other, you're going to break off the parts, break off the particles from one part of that, from one side. Whichever is softer will easily break off. And then what you might even find is that, especially if it is a material like, say, aluminum, aluminum can easily score very easily with compared to, say, steel or carbide type of tooling tips. So the tooling tip can get smeared with the softer material like aluminum, and which will actually reduce the effectiveness of your component, or of your machining process, or your final uh, part fabrication process. So if you're doing machining in air, you can see that if you're doing mild steel on mild steel, then you don't have very high, have very high frictional force, or it's described in terms of the wear coefficient. Suppose you had hardened steel on hardened steel, you can see that the K value is much lower. It's like 10 to the power minus 9. But suppose you had mild steel and on mild steel, then you will have 10 to the power minus 2 to 10 to the power minus 3. It's pretty high compared to 10 to the power minus 9. So you're going to create what is called the wearing of one side of your component with respect to the other, depending upon the relative hardnesses of the different materials. So for example, if it is the hard surface with respect to the smooth surface, so this smooth surface will chip off much easily compared to the hard particle. So the hard particle can kind of remove the material much more easily depending upon the machining speeds and things like that. So what levels of lubrication do you require in order to in order for it to apply to the manufacturing process? Say for example, if you are machining, between the tooling and the workpiece, you are going to have a very thick layer of lubricant, because if you don't, then you're going to create considerable wear of the particle and the tooling material. But suppose you had a thin piece, two thin pieces that are pretty much similar, then your lubricant layer does not have to be very thick. Sometimes you might also create what is called a boundary layer or boundary film on the two parts rubbing against each other, and that will help you to reduce the frictional forces between the two workpieces, the workpiece and the cutting piece. So for example, if you are trying to create uh, a radius on this bar, what you might do is um, you will create an internal conical surface that will rub against that and get that um, to be a very smooth surface and machined piece. So these are all different machining processes. I hope you have learned some. um, I'm not really sure if you guys have learned any other machining classes at all. But what you will find is that as this workpiece is turning, this um, roller is held on a rotating chuck, and that chuck will rotate. I mean, sometimes you might even put some kind of a sandpaper on that, or there could be individual pieces of sandpaper that are stuck to the rotating chuck, and that will cause a smoothness on the surface of your final machined piece. Or if you have a flat surface, you might have a different kind of a cutting. I mean, the burn. I mean, it's called this process is called burnishing. So you're burnishing and removing and getting the surface to be a very smooth surface. You may have a process by which um, you have some kind of a hot torch um, that applies some level of spray of molten pieces of metal. These molten pieces are going to be extremely small and thin. So it's like painting, I mean spray painting. So you are spray painting a metal coating on top of the molten metal spray on top of the final piece. And how does the molten metal, I mean, how does this metal get molten into smaller pieces? What you do is um, you are applying a wire rod and you have a gas nozzle that has the gas being burnt at a very high temperature, and that gas will melt the metal pieces or the metal wire, and that wire will create a stream of those metal particles that will go and stick onto the surface of your final part. So this process is called thermal wire spraying. You have another process which is called chemical vapor deposition. So here you have uh, some kind of a gas. So for example, if it is uh, it's called it's a silane gas, or it could be a chloride gas. So silane is methyl trichlorosilane. So it is a containing silicon, and when you apply some kind of a gas, like it can be argon or it can be some kind of a nitrogen, it goes in through that um, solution, and it will create some kind of a spray which is goes through a long tube that kept at pretty high temperatures. So when that happens, that spray will react with the gases, form some kind of a um, material. Say for example, if it is methyl trichlorosilane, um, methyl trichlorosilane will form particles of silicon carbide, which is one of the hardest materials known to us. So, and it will go and deposit in a very fine manner on top of the substrate material. Um, or if you had, say, titanium chloride, the titanium chloride, when it deposits, it will be depositing titanium metal. And the advantage is that the surface of your final piece or final part would be extremely smooth, and it will generate a very nice and clean surface. So that final surface, when it is being used to machine and things like that, it will provide very low amounts of friction. So it can easily move on top of the other surfaces and machine them. And the other advantage is that the silicon carbide or the titanium carbide would be extremely hard and abrasive with respect to the substrate material. You can also have, in order to get a very nice and smooth surface finish, you can also do what is called electroplating. I don't know if you have heard this or not. So you can put a coating of chromium or copper or nickel, etc. How do you do that? You have a cathode and an anode. Anode is the material on top of which you want to deposit uh, the ions from the solution. So for example, it is copper sulfate. Okay, and you apply some kind of a potential, and that copper sulfate will start depositing copper on top of the substrate material, and it will be extremely smooth and clean. And this is a process that is used a lot. um, and you might even do heat treatment at the same time, or after heat treatment you may do that in order to get the nice surface finish. You have another process called electroforming. And what is electroforming? Electroforming would be you take a mandrel with the correct size, and you machine the form of a bellows or some kind of a, say for example, if you have a groove that is on top of your final part. So what you might do is you machine that into this surface onto that it is, and this is called the mandrel. So you machine that bellows onto the mandrel, and then you electroplate material on top of the mandrel material, and then you would also trim it if necessary. And then what you do is you machine the mandrel that is inside through an etching process. So then you only end up with a final part that only has the material that is being electroplated. And common materials are like nickel and so on, nickel, copper, chromium carbide, etc. So for all these materials, you have to measure the surface finish. And how do you measure the surface finish? So it is measured by what is called a coordinate measuring machine. So if you go to any of the big manufacturing plants, you will have a coordinate measuring machine. And the acronym for that is CMM, coordinate measuring machine. That CMM will, you have some kind of a stylus, very hard stylus, and you move it on top of the surface for which you are trying to measure the surface finish. And you can do that on top of the any of those materials. And while it is being contacting the surface, that information is also being acquired from the stylus onto the computer, and it is that information is stored, and the software will also tell you what is the root mean square value for your surface roughness, etc. So you can also have some kind of a laser probe. So nowadays you don't use any kind of contact measuring machine. So you have a non-contact measuring machine. And what you do is you go and you click and put the laser depending upon the distance. And when you put the laser on the surface, it will tell you what distance you are at. and then you keep moving that laser beam, and it will keep telling you how far or how close to you are with respect to your starting point and how long you have moved and things like that. So based on that, you can measure the actual dimensions of your final part. So for each of these materials, you have different ways of measuring the tolerance and assigning the tolerance. So your drawing should tell you that. So your manufacturing process will tell you, for example, um, this nominal dimension should be approximately 40 millimeters plus or minus zero point zero 0.05 millimeters. So it can also be in terms of inches and so on. So it can tell you how many, like, how many microns or how many mils it should be, etc. So what is 1 mil equal to? 1 mil is equal to approximately 25 microns. So now there could only be, I mean, like, in this case, um, this one might say that, it should be 40.05 plus 0 and minus zero point 0.1 millimeters. So what does it tell you? It tells you that it cannot be oversized, it can only be undersized, and even the undersize has to be within a certain limit, etc. So why? Because in the application, it may not be able to accept any kind of oversize parts. So then you have to give it back and get it remachined or reground in order to remove that and get the value within the um, within the stipulated dimensions. So you can see that the tolerance and surface roughness in various manufacturing process. So for example, if you have a 25 millimeter workpiece dimension, so you can see that if it is a permanent mold, I mean, you can, I don't know if how easy it is for you to read. I'm not able to see this very clearly. So if you have broaching, then the tolerances are, you can get much finer tolerances. Whereas if you did just rough machining, then it might be pretty high. So how do you determine if you're um, if you are making, say, 100,000 parts, and how do you know if your manufacturing process is accurate or not? So you can plot the values that you get as a normal distribution curve, um, and it will tell you the range of standard deviation for your materials. So most of it, 99.73%, would fall um, within, say, 3 sigma or 2 sigma. What is sigma? Sigma is a standard deviation. So within two standard deviations, you will be able to get most of it within the limitations. But there could also be processes where you might want to tighten up the manufacturing process such that you do not have such large variations. So it all matters on how easy or difficult it is for you to manufacture. So if you have a very wide specification, that means your manufacturing process is not very accurate. If you want all of it to fall within the one or maximum two standard deviations, you have to spend the right amount of money, right amount of value to get those numbers. So if the more accurate you want it, the more closer to the average you need to, or the median you have to have. So for those of you who have done statistical product control or statistical SPC, or statistical quality control, you will see that um, you plot these numbers and you have an average value, and your process should tell you whether or not you should exceed it by 1 sigma or 2 sigma. So if it is above 1 sigma or 2 sigma, that means this part cannot be used and it has to be scrapped. So your process control should be such that you make sure that it falls within the range of, it should tell you how accurate your manufacturing process is. So depending upon the, so you have constants that are used in these. I mean, so from this you will be able to say whether or not your process is giving you the right kind of quality or not. Now, what are the factors that can affect your final part quality? So suppose you start with a very sharp tool. So after machining, say, 1,000 parts, that tool numbers are not going to be the same and they have to be replaced. So by looking at the quality control charts, you will be able to determine whether or not your machining tool gave you the right kind of dimension or not, or whether that tool needs replacement. So it might be that you will look at the quality control chart after every couple of hours, and it will tell you whether or not your tool is wearing out and how good your tool is to produce the parts within the limitations required or not. So nowadays, you will find that many of these have come with digital gauges so that you can get real-time data acquisition for SPC, I mean statistical process control and statistical quality control. So as it is measuring, you don't even need to interfere into the quality control process. It automatically does it. Okay, so that's about it, and I will upload this right now. Okay.